working assistant professor in the Department of Information Technology. Today we are going to discuss about AVL tree. Already people are knowing the concept of binary search tree. First of all, we need to know why we are going for AVL tree. What is the drawback in the BST? Then what is the necessity to go for AVL? So first I just want to explain about the drawbacks in the binary search tree. Let's see an example for that. Here I have taken some elements for the binary construction. Here are some of the elements to construct binary search tree. For example, my keys are like 4, 5, 6, 7 and 8 means I used to construct a tree like, see, my first element is 4, I will be taking that as the root, and my second element is 5, I will be start comparing with the root. Here the second element is 5, that is greater than 5, so I have to traverse right and I have to fix that element as the right child of 4 since it is greater than 4. Again take the next element, again start comparing from the root. So 6 is greater than 4, traverse right, again 6 is greater than 5, traverse right, and fix it as the right child of 5. Again you take the next element and do the same process. So again if I do the same process, I will be fixing 7 as the right child of 6. Again same way 8 will be as the right child of 7. So in this key distribution, I got a tree like right skewed tree. So sometimes we may not getting keys in a even distribution. We will be also getting a input like this sometimes. So if it is so, you will be getting the tree like either left skewed tree or right skewed tree. In this skewing tree, if I want to search for an element, say 8, I will be encountering the number of comparisons high. For example, I want to search for the element 8. So if I want to search for 8, first I will be comparing with 4. So number of comparisons is 1. Again I have to compare with 5. Again comparison, I will be getting the number of comparison 2. Again I will be getting totally 4 comparisons in order to reach 8. So first I have to compare with 4, like 8 is greater than 4, so I have to traverse. Again 8 is greater than 5, again I have to traverse. 8 is greater than 6, again I have to traverse. 8 is greater than 7, again I have to traverse. Then only I can able to reach the actual destination. So 4 times I have to do the comparison. So this is one of the drawback in the case of skewing. So that is the problem occurs in binary search tree. If the key distribution is not in the correct order, sometimes we may encounter like right skewed or left skewed. That time the number of comparisons will go higher if I want to do some operations like either search or delete or exit. So this will lead to the next version, say like AVL tree. So they have done some changes or variations in BSc that will get into another concept like AVL. So actually AVL is the abbreviations of 3 people, nothing but Adelson, Velsky and Lance. These 3 people developed this tree. The main aim of developing this tree is to balance the height. Here the height is somewhat higher. That's why we couldn't reach the data in time. It takes n number of comparisons. So if this tree would have been, arranged in a proper order in a proper height, then we won't be getting that many comparisons. So we are going to make the tree as a balanced tree. That's why we are going to learn AVL today. How we are going to balance the tree in terms of height, so that we can able to overcome this kind of situations. So we'll start AVL now. Here AVL is the variation of BS. So here we are going to follow the same properties of BST, but we are going to do one new thing, nothing but height balance situation. So AVL we can simply define like it's a self-balanced tree with the properties of BST. So we are going to follow the same properties of BST, but we are going to make it as balanced. So how we are going to make it as a balanced tree? For that, we are going to introduce the concept called balance factor, BF. So in order to find the balance factor, we will be using the formula like height of the left subtree minus height of the right subtree. This is the formula to find the balance factor. If the calculated value lies in the range either -1 or 0 or +1, then the tree is said to be the balanced BST, or like simply AVL. If the calculated value lies out of this range, then there occurs violation. So violation in the sense we will be encountering 4 types of violations. We will see there are 4 cases of violation. Case number 1 is alphas left child's left subtree. Violation number 2, alphas right child's right subtree. And violation number 3 is nothing but alphas left child's right subtree. And the last case is nothing but alphas right child's left subtree. Whenever we encounter a situation like alphas left child's left subtree violation, then we are supposed to perform rotation like single rotation and double rotation. So whenever we encountering problems like this, we encounter either one of this problem, here the remedy is nothing but rotation. Rotation is the remedy. So there are 2 categories of rotation, single and double. If it is a single rotation, we will be doing 2 options, either LL rotation or RR rotation. If it is double, we will be doing like LR or RL. L stands for left, R stands for right. So whenever we encounter either one of the situation, rotation is the only solution. Either we can go for single or double based on the situation. I will tell you in the next sequence. If it is left rotation, our action should be do right. If it is right rotation, our action should be do left. The opposite way we are supposed to do. And if it is double rotation, we are going to encounter left and right both. So if this is the case, perform left first and perform right next. Same way, if the rotation is said to be RL, perform right first and then left next. So these are the things to be considered whenever you will be constructing AVL. So the first thing is, as I told you earlier, AVL is a variation of BST. In BST, we got problem in the key distribution. If the key is distributed in a left skewed manner or right skewed manner, we will be having n number of comparisons. In order to reduce that, we are going for AVL. That's why it is also called a self-balanced tree or height balanced tree. The other name for AVL is, it is also called height balanced. Because due to the height factor in the skewing, we are having n number of comparisons. So to reduce that only we are going for AVL. So it is also called self-balanced tree or height balanced. So if we want to perform AVL construction, the very important thing you should know is the balance factor. Here the formula is height of the left subtree minus height of the right subtree. After the value is calculated, check the boundary value immediately. If it lies lies in the range like -1 or 0 or +1, then the tree is said to be balanced. If not, there occurs some violation. So the violation may be either case number 1 or 2 or 3 or 4. So that we need to find. Anyway, whatever may be the violation, rotation is the only solution. There are two types of rotation. Either we can get into single or double based on the situation. Under single we are having two categories: left rotation, right rotation. Whenever you encounter left rotation, do right. Whenever you encounter right rotation, do left. Same way if it is double, you may having the options like LR or RL. If it is so, if it is LR, perform left first and then right next. If it is RL, perform right first and then left next. So these are the assumptions you should have before entering into the AVL construction. So let's see one example. For this set of elements, say like I want to construct these three elements first. So take the first element. As usual, we have to go along with the properties of BST, because already I told you AVL is nothing but BST only, but we are going to add one parameter like height. Height is the main parameter and this is the AVL. So take the first element, fix it as the root. As soon as the element is inserted into the AVL tree, immediately calculate the balance factor. So balance factor formula already I told you, nothing but height of the left subtree and height of the right subtree. So we need to take the difference actually. So here it has no left subtree, no right subtree. So 0 minus 0 will be giving 0 only. Anyway, after calculating the balance factor value, we have to check the boundary. See, it is in the boundary only. So we can say the tree is balanced. Now take the next element. We have to go according to the property of BST. So take the next element, as usual compare it with the root. So 5 is greater than 2. So traverse right, fix 5 as the right shade of 2. Again, we need to calculate the balance factor from the first. After every insertion, balance factor should be calculated from the first. So here I will be calculating the balance factor for the recently inserted node. Always start calculating the balance factor from the bottom level so that you can able to achieve the height in the proper order. So balance factor is equal to, as usual, height of the left subtree minus height of the right subtree. So here it has no left subtree, no right subtree, so 0 minus 0 is 0. So the balance factor is 0 for this one, and for this one no left subtree, so 0, but there is a right subtree. See here I give you one hint. Whenever you want to know the height of the particular node, right, you just from the node take a longest path till the leaf and count number of edges. That will be one of the hint. It is easy for you to understand. So here for this particular node I want to calculate the height. So what I can do for this, from here I can take any longest path, count the number of edges. Okay. So here only one path is there. If I count the number of edges, only one. So 0 minus 1. This is height of the left subtree minus height of the right subtree. There is no left subtree, so I made it as 0. And for the right subtree, I placed 1 since the number of edges is 1. So here the value is minus 1. So the BF value for the node 2 is minus 1. Anyway, this is within the limit only. Still the tree is balanced. Now take the next element. Now next element is 3. So again 3 is greater than 2. Traverse right but less than 5. So traverse left. Fix 3 as the left child of 5. Again as usual start calculating the balance factor from the lower level. So every time we have to calculate the balance factor in order to make the tree as balanced. So again calculate the balance factor for the 0, obviously no left and right. Now we will take this one Here the hint is start from the respective node. You have to reach till the leaf. Take one longest path, count the number of edges. So I have considered this path. So from this node till the leaf I have taken one path. In that path only one edge is there. So my height of the left subtree is 1 minus, there is no right subtree for 5. So 0, 1 minus 0, 1. Anyway, this is within the limit. Again, for 2 I have to calculate reason. For 2 there is no left subtree. So now we are going to calculate the balance factor for the node 2. Since the node 2 has no left subtree, so our HL value will be 0. Now we need to calculate HR, nothing but height of the right subtree. See here, this is the entire right subtree for 2, right? So what I told you, whenever you want to calculate the height of a particular node, start from that node, take the longest path till the leaf and count the number of edges. So start from here, take one longest path, only one path is here. Reach till the leaf and count the number of edges. So here 1, here 2. So 0 minus 2, minus 2. See, minus 2 is not the value available in the given limits. So this is a different value. Immediately you mark it as alpha because this value is not there in the given limit. So immediately mark this as an alpha. That means we have encountered a violation. As I told you already, there are 4 types of violation, either case number 1 or 2 or 3 or 4. Now we need to check out we have entered which violation. Alright, see alphas, this is alphas with child. Always we have to consider with child. So alphas with child, right child. See alphas with child, that child in which subtree the recently inserted element is available. That has to be checked out. Right? This is a hint for you. Alphas with child, that child in which subtree the recently added element is available, because the recently added element is the cause for this particular value. Right? So if that is the situation, then just start doing the option like alphas with child, that child with subtree, the newly added element is available. See, alphas, right childs, this is the subtree. See, right child has only one subtree, that to left subtree, there is no right subtree. So alphas, right childs, left subtree, that particular element is available. So if it is so, what you can do now, I will give you a simple hint for every student because that is very easy for you to understand. Whenever you encounter a violation like double rotation, see here we have encountered 2 combinations, right? R and L. So that fall into the category double rotation RL. So whenever you encounter a situation like RL, you take these elements separately. No need to bother about the remaining elements in case if anything is there in some other problem. Okay. Here we don't have, because just we are having only 3. In some other situation we will be having many elements, right? That time we will be having some child elements here. Here also we will be having some child elements. That time you need not bother about those elements. I will tell you one hint. You just follow that. Starting from the alpha node, you consider the respective child node and form a triangle like fashion. This is a hint for you. Form a triangle, right? And you just separate these nodes which are involved in the triangle from the original tree and start applying RL procedure, right? As of now, we just forget about the remaining elements if it is for the other construction. Okay. Now, here perform single right rotation for the lower level elements. That means you do right for the lower level elements. See, if I rotate right, see here I am having 3, in this figure I am having 5. I am going to perform right. So if I once R is done for this, you start continuing for left. For the upper two notes, you perform L. So here in this figure I am having 2, in this figure I am having 3. If I do left, I am going to rotate left side. So if I rotate left, I will be getting like 3 here and 2 here and 5 here. At any cost, we should not violate BST. I told you very clearly, AVL is a variation of BST only. So BST should be strictly followed. So here see, lesser value is available at the left and greater value is available at the right. So we are not violating BST. At the same time, the tree is balanced. So this is how we can able to construct AVL tree. The remaining set of rotations will be seen in the next class. If you have any questions, you can put it in the comment. I will be discussing you. If you want any other topic to be discussed, that can also be pasted in the comment. I will help you. Anyway, the next sequence of rotations will be explained in the next class. Thank you.